Thank you everybody for sticking with us this long, and hopefully today we'll end with a bang, not a whimper. So today we'll talk about microbubble compatibility, and then we're going to switch topics a little bit and go into nanodrops, which are just another form of a microbubble. So I'll show you more what I mean. But first, let's get into microbubble compatibility. And just as a reminder of the application, so bubbles are being used as ultrasound contrast agents, target drug delivery vehicles, and oxygen delivery vehicles. So these are just three of the main applications, but you may find more applications. So I thought it would be good to start with a really, what I think is a highly inspiring TED Talk about focused ultrasound. Now this does not employ bubbles, but it discusses the technique of MRI guided focused ultrasound. So I think it's very informative, and it begs the question of what you could do if you add bubbles to this. So it also begs the question about biocompatibility of bubbles. So I'll show this. I put it with English subtitles, but I'll provide you with a link if you need a link to this, and you can get it with subtitles. I forget most of the major languages in the world. So, all right, we'll go ahead and start.
And the partners around the world are taking this idea, this concept, non-invasive surgery from the research lab to routine clinical use. This is what I'll tell you about. 13 years. For some of you, they can empathize with that number. For me, today, at this day, it's like a second of its So this dream is really enabled by the convergence of two known technologies. One is the force of ultrasound, and the other one is the vision enabled by magnetic resonance imaging. So let's first talk about ultrasound. And I hold in my hand the tissue indicating sensor is made out of silicone, it's transparent, made up for you, so you see it's all intact. Completely transparent, okay? I'll take you now to the acoustic lab. You see the factor within the alloy. This is a setup I put in the acoustic lab. On the right-hand side, you see an ultrasonic transducer. So the ultrasonic transducer emits basically an ultrasonic beam that focuses inside the phantom, okay? And when you hear the click, this is when the energy starts swirling, and you see a lesion form inside the phantom. Okay? So everything around you is whole and intact. Just a lesion form inside. So think about this is in your brain. You need to reach a target inside the brain. You can do it without harming any tissue. So this is, I think, the first kosher hypocratic surgical system. Okay, so let's talk a little bit about ultrasound, the force of ultrasound. You know all about imaging, right? Ultrasound imaging, and you know also about microbubbles, right? Breaking and kidney stones. But ultrasound can be shaped to be anything in between because it's a mechanical force. Basically, it's a force acting on the tissue that it converses. You can change the intensity, the frequency, the duration, the pulse shape of the ultrasound to create anything from a air brush, to an animal. Okay? And I'm going to show you multiple applications in the medical field that can be enabled just by focusing. Physically focusing. Okay. So this idea of harnessing focused ultrasound to treat lesions in the brain is not new at all. When I was born, this idea was already conceived by pioneers such as the Prof and Dr. who is known actually as the inventor of the gamma knife. You may not know know that he tried to perform the lobotomies in the brain non-invasively with focused ultrasound in the 50s. It failed, so he didn't invent the government. And it makes you wonder, why those pioneers failed. And there was something fundamental that they were missing. They were missing the vision. It wasn't until the invention of the MR and really the integration of MR with focused ultrasound that we could get a feedback, both the anatomical and the physiological, in order to have a completely non-invasive, closed-loop surgical procedure. Okay? So this is how it looks, the operating room of the future today. Okay? This is an MR3 with a focused ultrasound system. And I'll give several examples. So the first one is in the brain. One of the neurological conditions that can be treated with focused ultrasound are movement disorders, like Parkinson's or essential tremor. What is typical to those conditions, for essential tremor, for example, is inability to drink or eat cereal or soup without spilling everything all over you, or write logically so people can understand it, and being really independent in your life without the help of others. So I'd like you to meet John. John is a retired professor of history from Virginia. So he suffered from essential tremor for many years. And medication didn't help him anymore, and many of those patients were used to undergo surgery to have people copies of the brain. And about 4 or 5 months ago, he underwent an experimental procedure, which is approved under the IDE, the University of Virginia in Charlottesville, using focused ultrasound to ablate a point in his thalamus. Okay? And this is his handwriting on June 20th, if you can read it, 2011. Okay? This is his handwriting in the morning of the treatment, before going into the EMR. So now I'll take you through how a typical procedure like that looks like, how a non-invasive surgery looks like. So we put the patient on the MR table, we attach a transducer, in this case to the brain, but if it would be a different organ, it would be a different transducer attached to the patient. And the physician would then take a regular MR scan. Okay? And the objective of that, I don't have a pointer here, but you see the green sort of rectangle buckets. This is the sort of the general area of the treatment. It's a safety boundary around the target. It's a target in place, okay? So once those pictures are acquired and the physician has drawn, all the necessary safety limits and so on, he selects basically a point. You see the round point in the middle where the cursor is, and presses this blue button called sonicate. We call this instance of injecting the energy called sonication. The only handwork the physician does here is moving the numbers. This is the only device in this industry. So he presses sonicate, and this is what happens. You see the transducer, the light blue, this water in between this counter transducer, and it does this burst of energy. It elevates the temperature. We first need to verify that we are on target, right? So the first sonication is that low energy. It doesn't do any damage, but it elevates the temperature by degrees. And one of the unique capabilities that we leverage with the MR is the ability to measure temperature non-invasively. Okay, this is really a unique capability of the MR. It's not being used in regular diagnostic imaging. But here, you can get both the anatomical imaging and the temperature maps in real time. And you can see the points there on the graph. The temperature was raised to 43 degrees temporarily. This doesn't cause any damage. But the point is, we are right on target. So once the physician verifies that the focal spot is on the target that he has chosen, then we can move to perform, full energy ablation, like you see here, and you see the temperature rises to like 55 to 60 degrees. If you do it for more than a second, it's enough to basically destroy the against the cells. This is the outcome from a patient perspective. Same day after the treatment, okay? This is an immediate relief. John is one of like dozen very heroic, courageous people who volunteer for this study. And you have to understand, what is in people's minds when they are willing to take the risk. And this is a quote from John after he wrote it. He said, and his wife said, "This is the happiest moment of my life." And you wonder why. I mean, one of the messages I'd like to carry over is what about defending quality of life? I mean, those people who their independence, they are dependent on others. And John today is fully independent. He returned to a normal life routine. And he's also playing golf, like you do in Virginia, right? Where you are. Recovery. Okay, so you can see here the spot. It's like 3 millimeters in the middle of the brain. There's no damage outside. He suffers from no neural deficits. There's no recovery needed, no nothing. He's back to his normal life. Let's move now to a more painful stuff. Pain is something that can make your life miserable. And people are suffering from all kinds of pain, like neuropathic pain, lower back pain, and cancer pain from bone metastases, where the metastases get to the brain. Sometimes they are very painful. All those indications have already been shown to be successfully treated by Prof. relieving the pain, again, very fast. And I would like to tell you about PJ. He's a 78 years farmer who suffered from, how should I say, a pain in the gut. He had metastasis in his right body, and he couldn't see, even with medication. He had to forego, about all the farm activities. He was treated with radiation therapy, state-of-the-art radiation therapy, but you know, many patients like that take radiation therapy. And again, he volunteered to a pivotal study that we run worldwide, also in the US. And his wife actually took him, they drove like 3 hours from the farm to the hospital. He had to sit on a cushion, stand still, not to move because it was very painful. He took the treatment, and on the way back, he drove the car to Pakistan. So again, this is an immediate relief, and you have to understand what those people feel and what their family experience when it happens. He returned again to his daily routine in the farm. He rides his tractor, he rides his horse to the mountain cabin regularly, and he has been very happy. But now you ask me, but what about war? War and cancer. Show us some primary cancer. What can be done there? So I have good news and bad news. The good news, there's a lot that can be done, and it has been shown actually outside of the US. And doing that in the US is very painful. I don't see without this nation taking it as a something collective will, something that is a national goal to make it happen. It will not happen. And it's not just because of regulation, it's because of the amount of money needed under the current evidence-based medicine and the size of trials and so on to make it happen. So the first two applications are breast cancer and prostate cancer. They were the first to be treated by Prof. And we have better than surgery results in breast, but I have a message for humanity. We heard yesterday talking about the worst event rate in prostate cancer. there is a unique opportunity now with focus on guided biomarker because we can actually think about prostate lumpectomy, treating just the focal lesion, not removing the whole gland, and by that avoiding all the issues with potency and conflict. Well, there are other, capsule tools in the abdomen, quite lethal, very lethal actually, pancreas, liver, kidney. The challenge there with a breathing and awake patient, and in all our treatment, the patient is awake and conscious and speaks with the physician. Is you have to learn, teach the amounts of tricks, how to breathe in real time, and this will take time, this will take 2 years. But I have now a message to the ladies, and this is in 2004, the FDA has approved innovative focus ultrasound for the treatment of symptomatic uterine fibroids. Women suffer from that disease, with those tumors, have heavy bleeding during period, abdominal pressure, back pain, frequent urination, and sometimes they cannot even conceive and become pregnant because of the fibroid. This is Francis. She was diagnosed with a grapefruit-sized fibroid. This is a big fibroid. She was operated hysterectomy. This is an inconceivable proposition for someone who wants to keep her pregnancy long. So she elected to undergo a focus ultrasound procedure in 2008, and in 2010 she became the first-time mother to have the baby. So new life is born. So in conclusion, I'd like to leave you with actually 4 messages. One is, think about the amount of suffering that is saved from patients undergoing non-invasive surgery. And also the economical and emotional burden removed from their families and communities and the society at large. And I think also from their physicians, by the way. And the other thing I would like you to think about is the new type of relationship between physician and patient. When you have a patient on the table which is awake and can monitor even the treatment. In all our treatment, the patient has a stop sanitation button. He can stop the surgery at any moment. And with that note, I would like to thank you for this.
Okay, so see the convergence of 2 technologies, MRI and focused ultrasound. Now imagine what you could do with the convergence of 3 technologies, ultrasound, MRI, and microbubbles, right? They're heating the tissue, basically ablating it. It's like cooking the tissue, right? And that will work in certain applications. There's other applications where the idea is not to cook the tissue, but to deliver a pharmaceutical agent or maybe a gene, and then you get a positive effect. And so one can imagine going through the exact same kind of procedure where you have a patient, you make sure that the MRI, with the test run that you're on target, and then instead of juicing up the ultrasound so that it cooks the tissue, you do the bubble injection, and then you get the localized delivery of the drug, or just the mechanical action of the bubbles injection. And so that's kind of the whole idea behind focused ultrasound surgery with microbubbles. So every time I see that video, I always get a little bit teared up. It's amazing the technology and the impact it can have. And I think this is a good motivator that begs the question of our bubbles safe? Because, there was, like you said, historically, even in the 1950s, ultrasound was being tested as a therapeutic, but it could not come to fruition because there was no feedback control mechanism. So they needed MRI. They needed it in order to make it safe. And so the question is, when you have bubbles, is that going to be safe? Are microbubbles safe? So that's the big question about how to build it, right? So this is a recent paper that came out in 2015 by primarily cardiologists, right? So cardiologists in Chicago. By the way, these cardiologists hold a meeting called the Chicago Global Meeting every fall. So if you're interested in coming to the U.S. and learning more about clinical applications, particularly in cardiology, it's a good one to go to. And the name of the title of this paper is Update on the Safety and Efficacy of Commercial Ultrasound Contrast Agents in Cardiac Applications, which is what it was initially approved for in the United States. And so you can read this abstract, and it kind of gives you a nice overview. So I think it's worth reading really quick. So ultrasound contrast agents are currently used throughout the world in both clinical and research settings. The concept of contrast-enhanced ultrasound imaging originated in the late 1960s. That was an experiment by Gramiak and Shaw, where they were imaging with ultrasound the aortic root, and they accidentally injected some microbubbles. They thought it was a dye, was it an optical dye, indocyanide green, I think it was, and they originally thought it was this molecular dye, but then they realized it was cavitation bubbles from the way that they were injecting. You get a sudden expansion in flow, and suddenly release of pressure, you can get a cavitation. So there's short-lived cavitation bubbles, and that was in the late 60s. And that kind of spurred the whole idea, once it was determined that these were bubbles, to create your own bubbles, inject them, and use them as contrast agents. And the first commercially available agents were initially developed in the 1980s. Initially developed, it took another 20 years to get past. And believe it or not, those are, what was developed in the 80s and 90s are basically what's commercially available today. So again, they're quite crude formulations. I think from an engineering perspective, we can say that. Today's microbubbles are designed for greater utility and are used for both approved and off-label indications. This is kind of interesting, so that physicians can take an approved agent and they can use it off-label. If they don't get reimbursed by the insurance agencies, it's a good way for them to examine whether the technology will work in the patient population. In October 2007, so coincidentally, that was the year I joined as a faculty member, my first assistant professorship, and my research was focused on bubbles. And the very first semester, this happened. The U.S. Food and Drug Administration imposed an additional product label warnings that included serious cardiopulmonary reactions, several new disease state contradictions, and mandated a 30-minute post-procedure monitoring period. The agents, these were the only two approved agents that were in commercial use, opson and fluorine. Opson being a protein, fluorine being a lipid agent. And there was a point in time when Sanat Kumar was asking me, what if these bubbles don't really work out because of this? And you can imagine it was a little bit scary for me in the field and having this the basis of my research program that I was about to build. These additional warnings were prompted by reports of cardiopulmonary reactions that were temporarily related, but were not clearly attributable to these ultrasound contrast agents or microbubbles. Subsequent published reports over the following months established not only the safety, but also the improved efficacy of clinical ultrasound applications with ultrasound contrast agents. Okay. So the FDA received some reports. They reacted by putting a black weight box label on all the contrast agents, including this mandatory 30-minute wait period. And essentially the cardiologists pushed back and say, no, it's safe, you're overreacting. But they had to, of course, produce data to prove it. The FDA consequently updated the product labeling in June 2008, so you can imagine the relief that I felt a short while later, and reduced contradictions, although it continued to monitor select patients. In addition, a post-marketing program is proposed to the sponsors for a series of safety studies to further assess the risk of ultrasound contrast agents. Then in October 2011, the FDA leadership further downgraded the warnings after hearing the results of the post-market data, which revealed continued safety and improved efficacy. The present review focuses on the use in cigarettes. So basically, after millions of injections, these contrast agents are proven to be safe for patients. And this paper is a nice summary. It goes through, point by point through different contrast agents that are approved and commercially available. Here's a nice table that includes some. So Optisana, it's currently manufactured by GE Healthcare. It was first approved way back in 1997, so it was one of the first ones that was approved. Perflutrin, that's perfluoropropane, so C3F8 perfluoropropane. Intergas, and the outer shell is an albumin shell. So the albumin shell is what you guys produced in the laboratory during practical. That was bovine-derived serum albumin. They, of course, don't use bovine, they use human-derived serum. This is approved for LVO. LVO stands for left ventricular opacification. So these are patients where it's hard to see the left ventricle because of obesity or some other problem that the imaging would know. And also EBD, so endocardial border definition, marketed in the US and Europe. Then you have Definity. It's known as Definity and then also Luminity in Europe. And this is manufactured by Lantheus Medical Imaging. It was originally developed actually by a small company in Tucson, Arizona called Imarex. And I had the good fortune of meeting one of the people, Terry Matsunaga, who helped develop that this technology. Brilliant MVP, PhD PharmD scientist there. But currently it's marketed and manufactured by Lantheus Medical Imaging. It was approved in 2001. I'm not quite sure why they have another 2006. Maybe it's because it's for these other indications. Also perfluoropropane core, and it's got a lipid shell. Okay, and we saw when we talked about microfluidics, the work by Tim Seegers and Michelle Hirschlaus had looked at Definity-like formulations. So that includes dipalmitylphosphotylcholine, that's the main reagent, and there's dipalmitylphosphatidic acid, which is a negatively charged agent, and dipalmitylphosphoethylamine that's attached to the polyphenol glycol 500. So that's the reagent. It's approved for left ventricular opacification, endocardial border definition, also liver, kidney, and diagnostic assessment of blood vessels. Marketed in USA, Canada, Europe, Australia, and other parts of Asia, I think including India. There's also SonoView, or as it's known in Europe or throughout the world, or Lumason as it's known in the United States, for brachyl imaging. It was approved in Europe in 2001 and in the United States in 2014. It's got a core of sulfur hexafluoride, that's the core that you guys use with Biomedical. It's got a lipid shell, and it's also approved for basically the same indications, including breast. It's marketed in North America, New Zealand, Europe, Brazil, parts of Asia, including India. And then there's also Sonozoid, which is also owned by GE Healthcare, so they own an albumin shell and a lipid shell agent. It was approved back in 2007, perfluorobutane, and it's approved for liver and breast imaging in Japan and South Korea, so it's mainly just Asia. But I understand there's clinical trials in the United States for that as well. So those are the currently marketed ultrasound contrast agents. These post-marketing data studies are kind of summarized here. They tested both Definity and Optisana in the US, and they basically took this number of patients, 15,000, 3,000, and the results were no change in the mean PAP, pulmonary artery pressure, arterial pressure, and no deaths or SAE, serious adverse events, at 24 hours. Okay. So that was for DEFINITY as well as OPSLOT. So they've proven to be viable over the course of decades, over a decade. Almost 2 decades at least. Actually, 2 decades at least for others. Okay, so that's the safety profile. So what happens when you inject bubbles into the body? Well, we know number one that there's a gas exchange process. So we learned a little bit about that when we talked about gas exchange. So here's a little bit of information on biodistribution. There's a nice study that was done that compares liposomes and microbubbles. So you get a sense of the different pharmacokinetic profiles of these agents in the body. There's a study that was done in a group of Catherine Farrar. This is the group where I did my postdoc at UC University of California, Davis, and Michael and Artis is the one who performed the study. And it's a dynamic micro-PET imaging of ultrasound contrast agents and lipid delivery. So they used perfluorocarbon gas, perfluorobutane gas, a lipid shell, and in the lipid shell they had a PET agent. PET stands for positron emission tomography, and they had these short-lived PET probes, these isotopes that emit these photons that can be detected for PET imaging. And F18 is a really well-known PET probe. It's an isotope, a fluorine, F18. And then they conjugated that fluorine to a lipid, so FDP dipalmitoyl with the fluorine. So they show the symbol that looks like this. It's kind of the isotope, the nuclear sign, and then 2 acyl chains, both dipalmitoyl chains. So it was DPPC lipid, cholesterol. Well, for the microbubble, it was DPPA and DPPC and PEG 5000. That is the recipe for DEFINITY. For the liposome, they took off the PA and added cholesterol instead. So cholesterol is known to help stabilize liposomes in vivo. Okay? But it doesn't work so well for microbubbles. So first they just injected the probe, and this time it was dissolved in ethanol because it's a lipid, so it was dissolved in ethanol, and then they injected it into the body. So you can see it basically within a few minutes ends up in the liver of the human. This is in the body of a mouse, and it ends up in the spleen, and then subsequently, or the bladder. Sorry, that was the bladder. And then subsequently eliminated. So again, 30 seconds, 45 seconds. It's all over the place. But it's being mainly taken up from the liver. This is what happens to lipid. It gets taken up from the liver. Okay? So this is a good demonstration of that. One more time. You see the injection. Okay, 15 seconds. It's injected, it's circulating through the body, but rapidly being taken up in the liver. In the liver, it's broken down by liver enzymes, lipases, which are enzymes that break apart lipids, and then shuttle to the bladder for removal excretion. Okay. Next, they injected liposomes. So liposomes again are liquid filled interior, liquid on the exterior, so you have a bilayer, separate monolayer. The liposomes are injected and they circulate. They continue to circulate for a long period of time. They basically circulate throughout the mouse, the entire circulation, this entire circulatory system of the mouse. You particularly see them in the lungs, that doesn't have vasculature. It goes through the tail vein, through veins that go to the heart, and it gets screening throughout the body. After 30 minutes, it's still freely circulating in the body. Some uptake in the spleen, but most of it's still circulating. Okay, so here's microbubbles. Microbubbles get very different profiles. Initially, most of the microbubbles get taken up by the lung, and then they get shuttled to the spleen. And the spleen is like it's an organ that acts like a filter for the blood. It usually filters out like red blood cells that are spent, that are degraded, no longer functional. It's got this sinusoidal vasculature that has these resonant macrophages that are pouring out particles. So it tends to be an organ that really cleans out the blood, particularly larger particles like microbubbles. You can see it. It's getting caught in the spleen. Now this is what happens to bubbles. Okay? Within 40 minutes, most of the room is spleen. There's not much you can do to microbubbles to get around that, to change that. It's a product of the fact that they're well, the size that they are, the micron scale size, and that they can be phagocytosed by the liver, and the Cooper cells in the liver and the macrophages in the spleen. So this shows some of the biodistribution profiles. They did a maximum intensity. This is like a maximum intensity image. So these are the microbubbles. You can see it in the liver and spleen. The microbubbles at a higher concentration. You see some in the lung. Here's a blood vessel, and then the spleen of this mouse. And when it was in just a free agent of ethanol, mainly ends up in the liver and then gets shuttled to the bladder. And then liposomes are circulating throughout the vasculature in the heart, the spleen, see them in the kidney, and in the blood vessels. You can draw a region of interest, like around the liver, for example, and look at the intensity. So the percent injected dose per cubic centimeter as a function of time. This is often how ethanol is indicated. And so when the lipid by itself is an ethanol, you can see the different organs, but in blood, you can see, well, let's see, so here is the liver. You see it gets rapidly taken up by the liver and then cleared, and then in the kidneys, ends up in the kidneys, and then gets cleared through the bladder. Liposomes are here. They're injected. They get taken up into the blood, and they're still in the blood even after 90 minutes, hour and a half. Also in the lung, which is highly perfused, right? In the lung, because they're in the blood. And also in these other organs, liver, kidneys, spleen. So here's microbubbles. This is looking at the blood, kidneys, and spleen. So they're injected, and you see them initially in the blood, and then you see that decay rapidly over time. In the kidneys, they just as very similar to the blood, it's just a fraction of the cardiac output, and then the spleen. So they get rapidly taken up by the spleen, and that's where they reside. Also, the lung and the liver, you can see in the lung, they get initially taken up in the lung, and this may be because of that gas exchange phenomenon, right? So the bubble is initially injected, and it's got propane, butane, and support, and then it gets into the lung, and oxygen and nitrogen can fuse in, grow, and then get caught in the capillaries of the lung. There's also macrophages in the lung that can take it out. And then the lipid gets shuttled out of the lung subsequently. And as it's getting shuttled out of the lung, you see it increasing increasingly getting taken up by the liver. So there's an active process where materials can move from the lung to the liver. So this is what happens to the lipids when you inject them into the body of microbubbles. You see a lot of the lipid gets into the spleen, it gets into the lung, it gets shuttled to the liver, and subsequently degraded and excreted. So that's the lipid. The other major component of the bubble, of course, is the gas core. So what happens to the gas? Another nice paper published in 2008, and this was by a group that, so this was a study that was done in collaboration with GE Healthcare, and it was done in Norway. And here they're looking at pharmacokinetics of peripheral butane following intravenous injection and continuous infusion of sarnozoid. Sarnozoid is that lipid-coated peripheral butane bubble in healthy volunteers, that's humans, and in patients with reduced pulmonary diffusing capacity. So the question was, what if the patient isn't breathing well? Is there going to be an extra problem associated with that? So looking at the PK pharmacokinetics of the peripheral butane in healthy and sick patients. And they were able to use a gas chromatograph and mass spectrometer method to look at PFP concentration in both blood and in the gas that was exhaled from the lungs of the patient. So this is the PFP concentration in blood as a function of time. And this is the log scale, and this is the PFP concentration in nanograms per gram of the patient of blood. And this is in times, so 0 to 150 minutes. And you can see when it's injected, it's initially decreases. So there's an initial dip point here, and then it increases because of the bolus injection. And this is a bolus injection, so we also tested infusion. This is a bolus. And you can see it decreasing as a function of time. I should also point out that there's a difference between the healthy patients and the sick patients. This is a peripheral butane concentration in exhaled air. So again, this is the log scale of peripheral butane concentration in nanograms per milliliter as a function of time, going from 0 to 150 minutes. And you see it rapidly increases, which you can't really see on the scale, but then it starts to decrease extremely rapidly. And then they look at they basically measure these concentrations and use pharmacokinetic models to back out these pharmacokinetic parameters. And so they look in blood and exhaled air, they look at healthy volunteers, patients receiving the bolus versus the infusion of microbubbles. So you can suspend the bubbles and slowly diffuse them, or you can inject them all at once, that's a bolus. And they saw a bi-exponential decay, so the distribution, that's really how fast they leave the blood system. And so you can see that both in blood and in exhaled air is really quite fast. Well, I guess ignore the infusion because what's interesting is the bolus here, so just pay attention to the bolus. So you have about 2 to 3 minutes at the gases. It makes sense because we expect that when you inject these into the body, there's a gas exchange process where peripheral butanes going into the blood and subsequently to the tissue, oxygen, nitrogen, carbon dioxide are coming into the bubble. And then at the alveolar interface with the blood, there's no peripheral butane in the air, so that's always constantly coming off and being eliminated through the lung. And so initially the peripheral butane goes into the tissue and then it comes out. Okay? But it comes out of the bubbles very rapidly, in 2 minutes. That's the half-life. So this is a brief summary of these types of studies in humans. In 1999, peripheral propane was studied with optisone and they found it was eliminated within 6 minutes from the body. In 2008, we saw that study I just showed, peripheral butane. It's eliminated from the bubbles within 2 minutes. It's eliminated from the body within about 3 minutes. Well, that's the half-life. And then in 2001, there was a study by Correas, and that was, ooh, that's not right. It's not 112, it's 12. C5F12. Yeah, that breaks all the valence walls. But C5F12, so we go from C3 to C4 to C5. C5 is actually not an any FDA approved agent. This was back in 2001 when the group was developing an agent called Ecogen. Ecogen was a C5F12 agent that the phase transition is in between room temperature and body temperature. There's a vaporization temperature, 1 or 2. So it should be a liquid at room temperature, and then it should vaporize into a bubble at body temperature. And the idea was that this is great. We can store it as a liquid and then activate it and make it into bubbles right before the injection. But it ultimately was determined to be unsafe because it was too volatile and it was too hard to control that vaporization process. But anyhow, they did this and they found that a half-life to be of the C5 to be on the order of 2.5 minutes. Okay. So there's no correlation with carbon chain length and half-life because there hasn't been really a head-to-head study of all of them. It's just that each one has been looked at, and we know that each one is gone within a few minutes. Okay, it's gone within bubbles. Which makes perfect sense based on the modeling that we saw with gas exchange. Right? We expect there to be a gas exchange. I should say that the half-life of the microbubbles are much longer than this. They're on the order of 5 minutes to 10 minutes. So, one of the things that happens to bubbles is they get caught in the spleen. We saw that they got caught from the dynamic PET studies. And they also get caught in the liver. But different bubbles get picked up by the liver at different rates. And so there was a group in Japan that wanted to look at this. So they looked at phagocytosis of ultrasound contrast agent, microbubbles, by Kupffer cells. Kupffer cells are the phagocytic cells that reside in the liver. The liver, or liver cell. But they're phagocytic. They gobble themselves in the blood. And they looked at different contrast agents. So the story is a little bit different in Japan. So these are the commercial contrast agents. There's Levolist, which, and you have to be, I would look at this with extreme skepticism, the mean diameter, because we know these are polydispersed. So first of all, they're not a normal distribution, and second of all, they're polydispersed. So they should be really using a medium diameter, and they should be providing more information on the distribution of the agent. But here they say, well, somewhere between 2 and 4. They say no shell. We know that no shell is impossible. It must be stabilized in some way. It has an air core, and they say it has a negative charge. Okay. There's Optosan, which has a bubble diameter between 3 and 4.5, maximum up to 32 microns. Okay. These are ballpark numbers, right? Polydisperse. Human serum albumin protein, octapropane or propane, slightly negative charge. Imavix, or Imagent. Imagent is a really interesting one. It's been FDA approved, but it hasn't been marketed. So it's a really interesting agent that's been approved, but still out there. Larger diameter, 5 microns. The lipid is DMPC, which is quite interesting. So it's used as a shorter chain lipid. And it doesn't have an emulsifier, which is another interesting thing. And the way that they produce it, they don't use an emulsifier. It's got perfluorohexane and nitrogen cooling. So C5 at 12 plus nitrogen, which is interesting. We've sort of worked out the gas exchange. And it's got a neutral charge because it's only got phosphorylcholine, which is a low neutral. There's also Sonoview, smaller particle. It's made out of lipids, ESBC, DPPG, palmitic acid. These are the lipids that you know. macrogol 4000. And I think that's okay to 40,000. Sulfur hexafluoride, negative charge. Mainly because of the DPPG, glycerol is another negatively charged lipid. Then there's sanazoid, also small bubble, lipid stabilized, peripheral butane core, and negatively charged. Okay. And they did a study with just a microscope of some Cooper cells. So they got these Cooper cells from rats. So they got them from rats, and they plated them, and then they added bubbles, and they let the bubbles. So they flipped, they plated the cells on the cover slip, and then they flipped over the cover slip and injected the bubbles, so the bubbles would rise and interact with the phagocytes, the Cooper cells. And then they flipped it back over and washed it to see, and they had this fluorescently tagged bubbles. You can see here. So, okay, so they tested Sanazoid, Optosan, Levelbist, Innovist, Sono. And they see a lot of binding of Sanazoid and Optosan, not so much of Levelbist, Innovist, and Sono. They look at the comparison of phagocytic ratios of various contrast agents. So here listed are those contrast agents here. The phagocytic ratio, the phagocytic ratio, the way they define it is the number of phagocytes that had, percent of phagocytes that had a bubble. Okay. So Sanazoid, which is the lipid shell agent that has the butane gas core, or it's called GE, 99% of the phagocytes. Optosan is a protein shell bubble that is propane, also owned by GE, has also 100%, 99%. Levelbist, 50%. And then these two agents, Innovist, 0%. So this neutral DMPC coated bubble has sulfur hexafluoride, peripheral pentane gas core, didn't get much phagocytosis at all, undetectable phagocytosis. Some of you had a little bit, about 10%. So two lipid agents are showing excellent compatibility. One lipid agent showing horrible compatibility. This is number of microbubbles in one cell, 1 Cooper cell, so 6, 8, 2, 2, and then total microbubbles in 500 Cooper cells. So you look at these numbers, let's look at the maximum numbers. So about 4,000, about 5,000, 700, 0, about 100. That's kind of interesting. Innovist is a very interesting agent. Because the Cooper cells are taking up these bubbles, you can image the liver with these bubbles. Okay? So what you do is you inject these agents, and then you wait for the free agent to clear from the body, and the liver Cooper cells are taking them up, and after a while, they'll only be left in the liver. So here's an image of the liver. Levelbist and Sanazoid. Remember, these Sanazoid and Levelbist had a lot more uptake of Cooper cells. Some of you not so much, right? Some of you had like 10%. So we don't see much in the liver for some of you. And you can also take out those Cooper cells by adding gadolinium chloride. I don't know exactly how the mechanism works with gadolinium chloride, but somehow it destroys or removes the phagocytic capabilities of those cells. And a corresponding decrease in contrast agents seen from contrast from Levelbist, Sanazoid, and Sanazoid. So this is just sort of a negative control experiment. We knock it down. There's still some bubbles getting trapped, probably because they're getting trapped in the cytosines of the okay. So those are the basic. That's the basic biocompatibility of microbubbles. Okay? They're proven safe. When they're injected, the liquid gets taken up. They get taken up by the spleen and the lung, and then the liquid gets shuttled to the liver and degraded. Gas is exchanged with blood and then gets eliminated through the lung. And the different shells can affect the phagocytic capability of the pump. So different shells can be phagocytic to different things. The phagocytosis is particularly important for ultrasound molecular imaging because the goal here is to image a physiological state of the organism, of the tissue. And if you're having phagocytosis, and you don't know, is it because my bubbles are binding to some target receptor, or are they just getting phagocytosed by phagocytic cells like phagocytes, Kupffer cells, etc. So, it's an important consideration. Remember what ultrasound molecular imaging is. You check these bubbles are targeted, they circulate throughout the body. You point the ultrasound where you want to do the imaging. The bubbles are moving in the vasculature, but because of multiple ligand receptor interactions, they bind firmly adhere to the vasculature. And then you can see you get an increase in the signal because of these bound bubbles. And you do a break pulse to discriminate the bound bubbles from the free bubbles. Like you talked about that yesterday. So the problem is really complement binding and activation, because this is what ultimately leads to removal of the bubbles or phagocytosis of the bubbles. So what is complement? Well, complement are a series of proteins that are present in the bloodstream. Okay? And they're an integral part of the body's immune system. You can kind of see, here's a little bit of a cascade here. C3 is a major player in the complement cascade. And C3 gets converted by an enzyme called 3C convertase into C3A and C3B. C3A is a soluble factor that's in an anaphylotoxin. You ever heard of an anaphylactic shock? Somebody is allergic to something, and anaphylactic shock. That's because there's a high amount of anaphylatoxin in the bloodstream. Right? It stimulates the immune response. It's like an upregulator of immunity, positive feedback. And then C3b binds to the target. It's supposed to bind to target microbes, but viruses and bacteria. But it can also bind to your bubble. And then it interacts with these other factors and stimulates an immune response. Okay? That it's kind of interesting. You get this all these proteins come together and form this complex called a membrane attack complex on the back that then just basically creates a giant pore in the cell, in the membrane of the bacterial cell, and kills the bacterial cell. So it's part of what's called the innate immune system. So there's three known pathways, but two major pathways of immunity, the so-called classical and alternative pathway. Actually, I hate this definition because it gives you the wrong impression. The classical pathway is an antibody that binds to the pathogen that interacts through things and then eventually through C3 and C3b. Okay? The problem with classical is, and then there's the alternative pathway. The alternative pathway is that C3b binds to the pathogen, interacts with factor B, further stimulates more conversion of C3 to C3b, and there's positive feedback. Okay? And both of these pathways go through this positive feedback here. But the problem with this is the classical pathway is antibodies. Antibody, evolutionarily, is a more recent evolution of our immune system. The alternative pathway is actually older. It's the original immune system that we have. Sometimes we call it the innate immune system. It doesn't require T cells and things like that. So the complicated T cells, B cells, etc., are part of this. Whereas the alternative pathway is kind of this, this default method of clearing particles from the bloodstream. So C3, it turns out, is a problem. You know, C3 is converted to C3b. C3b binds to the bubble surface and further stimulates the positive feedback loop with amplifying cascade. That is, a small thing gets amplified into a big thing, right? With positive feedback. And it binds to nucleophilic groups on surfaces. So in 2006, Janssen et al. Elucidated the crystal structure of C3 and C3b, and they found in particular this thioester bond that is present. Now, normally this thioester bond is hidden in a pocket in a C3 molecule, but when C3 convertase comes and chops off the C3a, it reveals the C3, the thioester on C3b, and then that thioester is available for binding. And it binds to nucleophilic groups, like in particular hydroxyl groups. And this is really bad for well, it's good for the body's immune system, but it's bad for targeting because try to find a biological ligand that doesn't have a hydroxyl group. I dare you. This is like the simplest targeting ligand. It's a cyclic RGB peptide. Okay? So you're going to find carboxyl groups, carboxylic acid, right? You're going to find hydroxyl groups on all these kinds of sugars, etc., on basically any kind of biomolecule. So just look at this one, for example. There's a hydroxyl group, there's a amine group, nucleophilic, carboxylic group, etc. Plenty of groups on here through which that thioester can bond. Okay, so that's problematic. And then once C3b binds to the surface, then it can bind to a number of receptors. So these are the ligand, that's C3b, now present on the bubble surface. And and then it binds to CR1, CR2, CR3, and CR4. CR3, or C3A, or sorry, CR1, CR2, CR3, 4 are present on monocytes, neutrophils, eosinophils, basophils, natural killer cells, B cells, T cells, erythrocytes, even on platelets. You know what platelets are? Platelets are like part of the clotting cascade that's present in the blood. So you can see how you go from a targeted agent that's targeted to a specific receptor to something that's just targeted to blood and tissues that have white cells or macrophages. So this is why it's really important to think about the interaction of the agent with blood. So we approached this over a decade ago, this problem, that we need to worry about the ligand, but there is a solution to this problem, and that's what we call varied ligand architecture. So the concept of a varied ligand architecture is that you have a bimodal brush. So polyethylene and glycol have two different chain lengths, long chain and short chain. The short chain is tethered to the ligand, and the long chain has a methyl termination, so it's not going to bind to the complement C3, it's on the order of about 10 nanometers. When you form a bimodal brush, there's an interesting phenomenon that happens. You get the vertical segregation of the chains. The short chains get pulled in, the longer chains get pushed out. It's driven by the entropy of the system. It's an entropic effect. Basically, your big chains, your tethers on the ligand are short. They give you about a brush height of about 5 nanometers. That's internal brush height. And then you get an external brush height, an overbrush layer that extends out to 8.4 nanometers. So you can kind of get a sense of the structure. The lipid thickness is only about 3 nanometers. You can get a sense of the scale here, the size of the protein, and the size of the lipids. Again, here it is, the varied ligand architecture, short chains and long chains. And then there's what we call the exposed ligand architecture, which is the conventional, traditional way of targeting. you just have the same chain lengths, and then you put the target ligand on the end of it, and they're the same chain length. There's even papers that have this chain that's longer than the surrounding chains. So we showed that the buried ligand architecture reduces in vitro complement fixation. So we mixed it with complement preserved blood, and then looked at various different binding or different molecules at the surface. IgGs, albumin, and complement C3, C3b. We buy antibodies that are fluorescent tagged and do flow cytometry and see if they're binding to if these proteins are present on the bubble after you incubate in the blood. And we see with RGD plus the serum plus the antibody, we see a significant amount of binding on the bubble surface. This is the exposed ligand architecture. With the buried ligand architecture, we see very little binding. So imagine, so this is exposed ligand, this is buried ligand. Statistically different, much lower binding. So we looked at control, so there's no ligand here, 5% ELA, 5% ELA, exposed ligand architecture, giving much more complement C3 binding. You can actually see the neutrophils, the bubble binding to the neutrophils, a large bubble compared to the neutrophil, but you can see it, both on activated neutrophils and resting neutrophils. What was interesting is that the exposed ligand architecture actually seemed to activate the neutrophils, right? And that makes sense because when C3b binds to the surface, it stimulates convertase to convert more C3 into C3b and C3a. C3a is a nephrotoxin. It stimulates the immune response. It stimulates the neutrophils. This is bubble binding to neutrophils. Now, this is the ELA, the exposed ligand architecture. We see a lot of bubble binding. ELA, we see not much binding. Okay, this is with resting neutrophils and with neutrophils that were stimulated with intraluminal. So this is even though we pre-stimulated them, we still don't see the buried ligand architecture for this binding. What's interesting is what I don't show you here is that the target, the ligand in this case is not RGD, it's biotin. It's a vitamin. Biotin vitamin. So this is how prevalent the problem is with vitamin. You cannot find a ligand that doesn't have a hydroxyl group or some of the nucleophilic that won't bind to C3. It's just prevalent. We found that BLA reduces complement activation, so you can also look at soluble factors, C3A. You see the exposed ligand architecture, we get upregulation of C3A in vitro and in vivo. And as you might expect, the buried ligand architecture, since it doesn't bind to complement, and it's not activating the complement system, that the bubbles would circulate longer. So this is exactly what we see. You draw a region of interest in the rat kidney, and you look at ELA, the black curve, versus the ELA, the red curve. There's a significant difference, right? And the falls is consistent with controls. The BLA also increases the half-life of tumors. This is exposed ligand architecture. This is the buried ligand architecture. So significantly larger persistence with the buried ligand architecture. Again, we're testing, and that's true for both RGD and RAD. Remember, RGD binds to the target. RAD is a control, isotype control. Now, we've successfully shielded the ligand from binding to complement C3b. But you might be asking, wait a second, now it's not going to bind to the target receptor either. It's just a stealth bond, right? So why go through all the trouble of targeting it if it's not going to bind it anymore? And the answer is we can use a phenomenon called ultrasound radiation force. Radiation, ultrasound mediated adhesion to force the bubbles to interrogate the surface and they're binding to the receptors there. So ultrasound radiation forces are well known. It's a initially observed by the Borden brothers back in the early 20th century, and it was first realized by Paul Dayton and Catherine Ferrara in 1999, first explained the use of contrast agent levels with ultrasound. Basically, what happens is the bubbles are pushed in the direction of the propagating wave. They kind of move a little bit forward and a little bit backwards, but more forward than backwards. So in the direction of the propagating wave. And it's maximized at the bubble resonant frequency. Right? This is one of the methods that's used to separate bubbles of a certain size. But you can do this in vivo. These are fluorescent type bubbles in vivo, and a blood vessel, and a mouse. And you can see with the ultrasound on, and you can push it against the far wall because of the ultrasound. So this is a slide that was originally made by Paul Dayton. This shows a video that was done by Charles Caskey at the University of Vanderbilt University, and the simulation was done by Shakwei Zhao at UC Davis. And this is the Rayleigh-Poiseuille equation showing bubble oscillations, and you can see its large enough degree of expansion and contraction that the bubble experiences. Okay, it's getting pushed, so this also considers the displacement of the bubble. It gets pushed about that far, or in this pulse. Okay, but you can see the large amount of expansion and contraction, right? So it's not just that you're pushing it against not a static particle, but it's expanding and contracting. You can imagine when it's expanding, it's revealing the ligands so that they can bind to the target. This shows a streak image that shows the oscillations of the bubble and the displacement of the bubble under radiation force. Significant amount of dilation that exposes the ligand. In fact, we did see the bubbles bind the fluorescently labeled bubbles that bind to activated Uvex cells. This is targeted adhesion in vitro. This is the focal spot of the ultrasound transducer. We see a lot of binding. We don't see a lot of binding outside of the focal region. And you can zoom in, you can confirm that these are indeed intact bubbles. You can see that they're intact under bright field because there's a big difference in index of refraction between gas bubble and surrounding medium, so they show up really nice in bright field. So this is a quantification of that data. When you use the exposed ligand architecture, you're getting a lot of binding both in the static case, that is when you flip the plate over and allow the bubbles to come up and get in contact with those Uvex cells, and then you flip it back over and you wash it. You see a lot of binding, and then when you apply radiation force, you see about the same amount of binding. This is a large scale. With the buried ligand architecture, you don't see any binding in the static case. The bubbles have risen up, they're interacting with the cells for a long period of time, like 5 minutes or something like that. Flip it back over, and they just float away. Whereas when we push them with radiation force, they bind at the same rate or the same density as exposed ligand architecture. So we employed this in vivo for actual in vivo imaging. We have buried ligand architecture, we have RGB versus RAD, and we have plus and minus radiation force. This shows the scheme, how we did it. We did it with the clinical scanners. You can do this, you don't have to have a fancy ultrasound system to do this. You can do this with clinical scanner. You do the local injection, you do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, ultrasound radiation force scans over the tumor. Then you do imaging, you do bubble destruction, you do another imaging, you do a subtraction to get the bubble, the bound bubble image, and then you allow them to clear. So you can see a big difference with the RGD plus or minus ultrasound. See all that green in there versus here? I don't know if you can see it very well. It's there. Then you can also see the difference between RAD and RGB, much less binding. So the control bubble is not binding. And the target bubble is only binding when you apply the radiation force. So this is some quantification of that data, decibels, BLA bubbles, minus radiation force, plus radiation force. You see binding versus RAD control, how much binding. This is kind of your level of background. And this is a ratio to give you a sense. So VLAs get a lot more. Basically, the ratio with and without radiation force is 1 for exposed ligand, but with the buried ligand, you see a major increase. Okay, so we're starting a study with canine patients using this. It's a combination of chemotherapy and anti-angiogenic therapy in soft tissue sarcomas. We're actually getting started just this month on this. We've been planning for a long time, getting all the technology, like the vet clinic that has there. We're starting to recruit patients. But I still think, there's always that ability to come back and re-engineer and improve the formulation. So size, cell stiffness, stability, etc. And ultimately, I'd love to see multi-targeted imaging. That is, imaging that you can do based on different acoustic resonances. So you can not only look for one target, but look at multiple targets at the same time. Multi-target imaging. Okay, so that's it. That's all I have for biocompatibility presentation. Anybody have any questions on that? So, last lecture, nanodrops. So we started with the young Borden Kelvin, and it's called blow the silk bubble and observe it. And we studied all your life and draw one lesson after another in physics from it. Now we're at the end of the session, and Borden Kelvin is an old man, but he's still learning. So I'll say not only silk bubbles, but nanodrops too. So remember that microbubbles are highly echogenic, and it's by virtue of the gas core of the bubble and its ability to compress and expand with the acoustic wave, and the fact that it can have resonance to the environment, and not only your oscillations, that allow it to be detected. Well, there's another method of generating bubbles that can be done in situ. It's called acoustic droplet vaporization. And the concept here is that you have these droplets of liquid, and these liquid droplets are small enough that they can circulate longer, like liposomes kind of in circulation, and they can also have what's called the enhanced permeability retention effect of leaky vasculature of tumors, in taking up into the parenchyma of the tissue. And then, by virtue of the ultrasound, we provide enough energy to vaporize the droplet into a bubble, and then that bubble can then facilitate drug delivery or can be used for imaging or something of that nature. So how do you make a good acoustic droplet vaporization droplet that experiences? And we faced this question a long time ago, almost a decade ago, and the answer that we came up with is, why not start with the bubble and condense it down into a droplet? That way, when you go back and form the bubble, you'll end up with the bubble that you started with. So you can control the final vaporization state by starting with that state in the first place. The idea is you take a perfluorinated gas like butane, and cool that and pressurize it to condense it into a droplet. And when you do that, the thermodynamics say that based on the molecular volume of butane on a liquid gas state, you should expect a roughly 5-fold increase in the diameter. So you start with a 4-micron bubble, you'll go down to an 800 nanometer droplet. You start with a 1-micron bubble, you should go down to a 200 nanometer droplet. So if you look at the phase diagram, you have the gas state, liquid state here. You have the temperature on the x-axis is Kelvin, pressure on the y-axis, kilopascal. It's the phase diagram, equilibrium phase diagram, liquid state and gas state. So you start with a gas bubble, cool it, and then pressurize it to make it into the liquid part of the phase diagram, and use that to condense the bubble. it's actually not cool, it's actually heated to 44 degrees Celsius in this case. And we pressurize it. So we go from, that's atmospheric pressure in Boulder, Colorado. And we pressurize it at 300, about 40 kilopascal. We see a reduction in size. And we're doing this a lot faster than what I showed you for the pressurization studies before. So these bubbles are experiencing more compression, less dissolution. The faster you compress it, the more you're actually compressing it rather than dissolving the bubble. And then eventually, you reach a pressure at which the gas core disappears and you just get a drop. And we can plot that as a function of temperature, the pressure that's used to move to that phase transition as a function of temperature. And what we see is, that, for example, for C20, that is lifted from, so here's the equilibrium phase diagram, and we're seeing the bubble is actually condensing at a higher pressure than we expect. If you recall, we said earlier that that could be happening because the shell has an elasticity that's leading to a pressure drop between the exterior exterior medium and the interior of the bubble. That may explain the pressure drop that's in here. So we looked at bubble condensation, and we also looked at vaporization. And this is the chamber that student Paul Marshall built to look at vaporization. So it's a chamber here. It's made out of stainless steel, and it's got some ports, so you can put stuff in the chamber, pull it out. It's got an observation port, which you can pass light. There's a inlet port, another port is the thermocouple ports, you can monitor temperature. Put bubbles in, pull bubbles out, this extraction port. And basically you place this chamber in the path of a laser. So the laser passes through the window, through the sample, through an attenuator into a photodetector. Photodetector is then hooked up to a data acquisition board. It's a linear value, and then we also have temperature measurement. So the lab is also controlled by a PI, not a PID control, but it's PI control. We're also measuring the pressure and controlling pressure with the pressure gauge. It also feeds into the depth. The way we do this experiment is that we initially have bubbles, so the bubbles are going to be scattering the light. So we get a reduction in the light, and then we pressurize them. So when we pressurize them, we condense them. And we hold them under pressure and heat the chamber to the desired temperature. And then once we reach the desired temperature, let it sort of stabilize, the temperature flatten out. Then you suddenly release the pressure, and there's a rapid decrease. So when you condense the bubbles, you lose the light scattering. So the laser is able to move through and you get a higher intensity. And then when you release the pressure, the droplets start to vaporize, and as they're vaporizing, they're starting to scatter the light, so you see a drop in the intensity. So this is the vaporization curve, part of the curve right here. And then, after they vaporize, they start to dissolve at this higher temperature. So we use often, like this is a pretty high temperature, so the bubbles are dissolving because their shell's kind of fluidized. So it's no longer able to sustain that very low surface tension. So the bubbles dissolve. So this part of the curve is bubble dissolution. And we fit the experiment to a theory for vaporization and dissolution. Just using a line explanation. And if you look at there's K1 and K2. K1 is the vaporization, K2 is the exponent for the rate of dissolution. So we're focusing on just the vaporization rate. And you can construct a Arrhenius type plot by taking the natural log of the rate and plotting it versus the inverse temperature. And then you get the data points and then you fit a line. and that gives you an activation energy. So this is like the activation energy to vaporize your droplet. And this energy is the energy. This is really the rate at which the bubbles are forming. Okay, so once you initiate the process, this is the rate at which they're forming. So this is the activation energy as a function of base chain length going from C14 to C24, and the theory predicts that you should see like a line, right, a linear increase with basal chain length. Because here you're just increasing linearly the van der Waals attraction of the chain, and so you would just expect a linear increase. But in fact, we see a sharp increase up to C20 and then a decrease. And this part is really consistent with the data that I've shown you before. Remember that we saw with C24 that those bubbles didn't circulate as long in vivo. We saw with C20 that those bubbles had lower elasticity. Okay, so this is probably, again, the same sort of, has the same basis, which is different microstructures in the phase separation, leading to these two lipids not stabilizing as well as we would expect. C20. So right now, our lab is really focused on C20, what we consider to be the best lipid. If you look at the magnitude of this energy barrier, it seems to be related to, it may be coincidental, but you can actually estimate how much energy it takes to create a fold based on the cohesive energy of the lipid. Okay, so and so if you imagine a bubble that's condensing, this lipid is already packed together and has to form these folds to condense, but then when it revaporizes, then you have to get these folds that reincorporate back into the layer. And the growth of the bubble, the rate of the growth of the bubble will depend on the rate of growth of this lipid, or this ability of this lipid to re-enter the monolayer. So it's going to involve whether the mechanism is a fracture or spreading mechanism or just a simple bending and zipping mechanism. You still have to overcome these intermolecular van der Waals attraction to break those and reform them. So it seems to be consistent that the magnitude of this and the trend seem to indicate that the intermolecular forces are playing a role. What's kind of neat about this experiment is that you can, so you start with bubbles, pressurize it for droplets, and so the pressure is actually blue here. So you pressurize and then release the pressure, you vaporize, you pressurize again, release the pressure and vaporize, and the intensity follows exactly. So this is a reversible process. You can condense, revaporize, condense, revaporize, and you're getting very similar results in terms of the intensity through this pore. So you can see this is an example. So here the pressure is relieved, you form the bubbles. The bubbles start to dissolve, and then they also float. So pressure is increased, and you condense all those bubbles into droplets. So you don't see any scattering. We're looking at an angle here, so if it gets bright, that means there's a lot of scattering. Pressure is relieved, we see a lot of scattering. So bubbles are formed throughout. So it's a very reversible process, actually. It's kind of interesting. But we looked very carefully at thermal activation of lipids, and then we looked at the peripheral carbon core. And one thing that was interesting was the ability to tune the temperature at which the particles vaporize, at which the droplets vaporize, by using mixtures. So there's a certain temperature that C3F8 will vaporize at, there's a certain temperature that C4F10 will vaporize at. It turns out that ideally you would be somewhere in between those. So can we get there by using a ratio, by using a mixture of those two? Okay? So you can make a mixture simply by using, you have your C3 and your C4, and they're both coming in at, and then you have them coming out of the canister and flowing, and then you use a rotometer to get to fix the relative flow rates, and then that will give you the mixture at the percentage that you want it to be at. And then you flow that over your bubbles or over your solution before you sonicate, or you use that in your vial and you shake the bubbles. And so these are the results of that experiment. So we increase temperature from 30 to 80 degrees Celsius or 70 something degrees Celsius. And we look at the percent of vaporization based on the intensity that we showed before. And C3F8, you see vaporization at the lowest temperature, and C4F10, you see vaporization at the highest temperature. And then the mixtures fall in between. So this worked really well of tuning the vaporization temperature. If you look at the 50% line here, where these values cross the 50%, it follows a nice linear scale with increasing C4F10 content. So the 50% line increases linearly with C4F10, and it fits really nicely right there. So the vaporization pressure, again, seems to be following this nice relationship with C4F10. This is just another way to analyze the data, but it's basically the same thing. So we thought, okay, great, we can tune the vaporization threshold. So let's see if we can do this in vivo. Let's see if we can utilize this. We didn't go quite in vivo yet because we hit in vitro and we had to stop, and here's why. We set up a tank with an ultrasound transducer that is imaging in contrast mode, and then we have a tube where the bubbles are flowing through, well, the droplets of the determined bubbles to vaporize the bubbles. It's in a heated water bath where we can control the heat, and everything's connected with lab there. And this shows the tube. You can see the reflections from the top and bottom of the tube. And initially, droplets are coming through. And when we reach a high enough temperature, I don't know if you can see that, but then you get a lot of vaporization that shows up as a large increase in the contrast intensity in that region. So as the temperature was increasing here, you get the vaporization, okay? But then, as the temperature continues to increase, you also get dissolution of the liquids, okay? So they become unstable. But this is happening, this is sped up in time. The process actually takes a lot longer to unfold because you have this tank that you're heating up, right? Okay, so here's the contrast intensity as a function of temperature, and you see the vaporization and then the dissolution of the bubbles. So here at baseline, you see very little contrast, and here at the peak, you see a lot of contrast. If you take that temperature at which you see that peak there, and you plot that as a function of, well, even the inflection point versus the content of C4F10, here's the line that we had before in the closed system that we dealt with before. But in this case, we see it rise up to this line for C4F10 very quickly. So even the 50% C4F10, even though this should have 50% propane, C3 in it, it winds up acting like a C4 bomb. So why was that? Well, we went back and checked it again, and this time we held it at a constant temperature, but we're changing the mechanical index. This is easy to do on the ultrasound device using the mechanical index. And again, same system, and you can see here they're vaporized. So let's see if we can. Okay, so we're increasing mechanical index, and nothing's happening, and then keep increasing mechanical. Finally, you started to see vaporization at a certain mechanical index. So you plot mechanical index on the x-axis, contrast on the y-axis. nothing happens at the low mechanical index. As soon as it starts to vaporize, you see a rapid increase in contrast, it levels out. Take the inflection point there, and then plot that inflection point. Here, that mechanical index, plot that now as a function of C4 of 10. And again, you see this at two different temperatures. 37, you see it increasing and flatten out. At 60 degrees, of course, a much lower mechanical index is needed at a higher temperature. Vaporizes droplets, right? That makes sense. But again, we're seeing this behavior where it's kind of like jumping up and flattening out rather than a nice line. And so, if a bubble that's supposed to be 50% perfluorobutane and perfluoropropane acts like a perfluorobutane bubble, then what's going on? So we thought, well, maybe what's happening is that we're getting a selective dissolution of the C3, the more soluble species, and then an enrichment of C4, lower soluble. And you can so look at that mechanical index for the inflection point versus the amount of time that we leave the droplets in the tube. And lo and behold, you see here's C4 of 10, it fits that line pretty well. But in mixtures, as you give them more and more time, they start to approach that line. They start to approach not that line, but the value of pure C4 of 10. Again, indicating this is real evidence indicating that the C3 is selectively leaving. So we modeled the content of the bubble core just using a model for bubble, in this case, droplet dissolution. And we have multi-component dissolution. And then we look at two cases, 50% C4 of 10, 25% C4 of 10. And this is time on the x-axis. In the log scale, you can see that we get a rapid enrichment of C4 of 10 as a function of time. And these are for different degas ratios between 0.9 and 0.99. You can see that there's a rapid enrichment. And the radius of the bubble starts to shrink, and there's kind of this dual mode. You see the loss of the C3 F8, and then the loss of the C4 F10. Okay, so basically what happens is in an open system, the C3 can dissolve and then you lose that. So you can't really use mixtures very well. You can use it in a closed system, okay, because you get equilibrium. So C3F8 is leaving the droplet as quickly as it's entering the droplet. So overall, you can it's a mixture that's stable. But in the open system, you get the C3F8 is leaving faster than it's coming back in, so you get an enrichment of C4F10. So you wind up with C4F10 droplet. Nevertheless, even if you use the pure components, you can definitely get a difference. So C3F8, you see it vaporize at both temperatures, 37, bottom temperature of 60 degrees, which is the temperature you might want to reach in a high-freeze situation. And C4F10, you don't see vaporization at 37, but you do see it at 60 degrees. So you can still use this as a probe of temperature, but you just can't use mixtures between them. Because in the open system, and the body is an open system because you're breathing in the atmosphere. You can't use the mixture. So, yeah, the field was thinking of using the we also utilized those gold nanoparticles that I showed you before for optical vaporization. So we had nanoparticle coated bubbles like we had before, but again, we then condensed those bubbles into droplets by cooling and pressurizing. And then we end up with nanoparticle coated droplets, the liquid form. So we put them under this photoacoustic setup with a pulse laser that's activating the bubble. We have a continuous wave laser that's tracking, or actually it's the droplet. Continuous wave laser that's monitoring the droplet. And then you can change the fluence of the laser and find out you can have it vaporized with certain laser fluids. Okay? So in this case, we have a laser fluids of 20 millijoules per centimeter squared, and there's no vaporization, so there's a steady amplitude. But when we use 22 millijoules per centimeter, it's enough optical energy to vaporize a droplet. So you see it vaporize, and look at it, you can actually see it bringing down. So you form a bubble, it vaporizes it into a bubble, and it moves down. This is microseconds, and by virtue of it using the continuous laser. So you can look at these, you can model these radial displacements, and from that you can get resonant frequency and so forth. What's kind of interesting, so we were able to make C3, C4, and C5, and this is the percent of bubble of droplets that vaporize as a function of fluence. So you often see this log normal type distribution, but you can see that the median diameter, or the median, fluence is increasing from C3 to C4 to C5. There's also, what we did not see is a size effect. So basically, before and after vaporization, we're seeing similar size distributions, in the vaporized bubbles. So there's this kind of idea that prior to this, that there's Laplace pressure that was stabilizing the droplet, therefore smaller droplets should be more stable. That's not what we observe. We see that small droplets are just as stable as large droplets. Okay, so from this, we kind of came up with some design rules for these microbubble condensed droplets. Use long phosphorylated chains, C20. The core, choosing the core is based on, instead of using the boiling point, we actually use the critical temperature of the core part. And for homogeneous nucleation, it should vaporize at about 90% of that. And that's exactly what we see. And I'm going to show you some more data that supports that here a bit. It appears that rather than being a Laplace pressure that stabilizes these droplets against vaporization and allows them to be superheated, it seems to be the homogeneous nucleation, the activation energy barrier to homogeneous nucleation that's preventing these droplets from vaporizing into bubbles, allowing them to be more stable. And at this point, you hit what's called a spinodal, and you force the phase separation. You force a vaporization. To do the microbubble condensation, you need to rapidly pressurize, otherwise you'll get dissolution. Right? Dissolution is going to have, the longer it takes you to pressurize, the more dissolution you're going to have. PFC mixtures work great in closed systems, but they do not work in an open system, so they do not work in vivo. So they're less practical value in that sense. And the phase change can be triggered by different stimuli, it can be by temperature, for example, hyperthermia. So if you have a situation like microwave therapy or some kind of hyperthermia therapy, you can use this with ultrasound to monitor that. You can use ultrasound to trigger and that's acoustic droplet vaporization using ultrasound. What's interesting is there's a phenomenon called superharmonic focusing that was elucidated by the group in the University of Twente that indicates that there's some focusing capability because of the spherical nature of the droplet that focuses the ultrasound waves, the higher frequency ultrasound waves. That's why it's called superharmonic, because it's higher frequency components of the pulse. Those higher components, frequency components are being focused, and then there's a higher component pressure, and that's what sparks the vaporization. And we also show that you can use a laser pulse with cold nanoparticles. So again, the laser heats the nanoparticles, the particles dissipate that heat into the core then heats up, vaporizes due to the surface plasma resonance of the gold nanoparticles. Okay, so let's dig into the chemical engineering thermodynamics and kinetics of the process. So we published this paper just a little while ago, 2006, Advanced Technology of Science. And this is really culmination of a PhD work from Paul Montfort. And what he basically argued was that Laplace pressure is not the mechanism by which you're stabilizing these droplets, allowing them to be superconducting. It has to be homogeneous nucleation. And the first argument is that if indeed it has Laplace pressure like you say it does, then that bubble is going to dissolve, or that droplet will dissolve. And so we showed these are droplet dissolution curves. They look like bubble dissolution curves. They accelerate, right? Dissolution. And these are different surface tensions on the interface of the droplet. So C3 and C4. But you see in both cases, within a few minutes, it's gone. Even if you started with relatively large droplets. Smaller the radii, the shorter the time. It just doesn't fly. I mean, from a mechanics point of view, sure, you can pressurize a droplet and it will be stable at up to higher temperatures. Okay? From a mechanics point of view, yes. From a thermodynamics point of view, a mass transfer point of view, if we consider the fugacity or the chemical potential gradient, that bubble that droplet has to dissolve. You just impose a boundary condition that forces that droplet to dissolve. Okay? So whereas our colleagues in electrical engineering and biomedical engineering with electrical can sit there and say all day that it's stabilized by Laplace pressure, chemical engineers, we're not going to let them get away with that because we understand transport and mass transfer. So this is a necessary thing. When you apply the Laplace pressure, it must dissolve, right? Okay, so we went back and looked at intermolecular forces between C3 at 8 and C4 at 10, and we can do coarse-grained modeling and get these kind of Leonard-Jones potentials and different orientations of the molecules and so on. This is parallel, this is anti-parallel. So parallel, of course, you get the maximum attraction force, here you get the minimum attraction force. So you kind of see the difference in those curves. And you can actually use these Leonard-Jones potentials with the van der Waals equation of state to determine the pressure volume curve. And when you do, you get this kind of weird behavior where, for example, as you're increasing the volume, or let's say decreasing the volume, you initially the corresponding pressure increases and decreases and increases. And so this region is unstable, and you can draw a line that separates these two partitions these into equal states, saying they have equal chemical potentials in the liquid and vapor state of equilibrium. And then you can use this line to establish the vapor-liquid equilibrium. So you can, from first principles, you can actually derive the vapor-liquid equilibrium plots for these fluorocarbons. So you have a liquid state, a vapor state, a vapor-liquid equilibrium state, supercritical state. So, and you can derive the critical temperature, or the phase delineation between the vapor state and the liquid state, and it goes up to the critical temperature, right? So that's the point. So this is the actual measured one, and it obviously falls in between the orientations of parallel and the parallel orientations of the molecules, right? Because they're going to be interacting. Okay, so you can establish that equilibrium line, and you can use different bubbles of different pressures, of different Laplace pressures by changing the size of the bubble and the surface tension of the bubble. And you can establish this liquid equilibrium lines and compare it to theory. And basically, again, this is the Laplace pressure theory. It predicts that as you get to smaller bubble diameters, that the boiling point should increase. This is just basically the Antoine equation, right? But the pressure now is coming from a loss pressure. These are different lipids, or different fluorocarbons, C3 and C4, at different temperatures. These are the gradations. This is the boiling point. This would be the peak negative pressure of the ultrasound that would be required, megapascal. So we're arguing that this is not, this is the explanation that's been given, but this is impossible. You cannot have a certain loss pressure on the droplet or it will dissolve. Okay? So it has to be something else, and we looked at the activation energy barrier or homogeneous radiation. So what that means is you have, if it's condensation, you have a gas or fluorocarbon, and those molecules are moving around and they're colliding, and sometimes they collide and they stick, and sometimes enough of them stick to form what's called a condensation droplet embryo. And if that droplet embryo is large enough, if it's too small, it will break away, but if it's large enough, it will continue to grow and eventually nucleate and condense the entire vapor phase into a liquid phase. And this shows, this is the nuclear radius. This is the delta G. You can calculate the Gibbs free energy gradient. And so what happens is as you get bigger and bigger nuclei, it requires more and more energy until you hit a peak, and then it drops off. So this is your what's called the critical radius, the critical embryo radius. So you can create embryos of that size. If you create an embryo of that size, then as it continues to grow, delta G goes down. That's a spontaneous process. So this is really your energy barrier for vaporization, to initiate vaporization. Now, we talked earlier about an energy barrier that we got from kinetic data about the reincorporation of lipid into the membrane. It's different. This is the initiation of the vaporization process. And you can actually, there's theory on that we estimate the embryo flux, okay, the rate of the creation of embryos, and as a function of different pressures, this is the pressure inside the bubble divided by the saturation pressure of the core. And when it reaches a critical embryo flux, it experimentally determined also about 10 to 20 embryos per second, that you will probably form a vapor embryo that's of sufficient size, the critical vapor embryo size, to initiate the condensation. And it turns out that it seems to fit. Here it is for C3, it's a lower pressure. Here it is for C4. So it may be one potential explanation for why it took higher pressure to condense those droplets. It could be that it's homogeneous nucleation. Or, alternatively, it could be that the bubble shell has an investment. So we're still not 100% sure about exactly what but what we're much clearer, I think what we're very confident about at this point is the vaporization. So that was condensation before, here's vaporization. Now we start with liquid phase. And in the liquid phase, again, the molecules are moving, they're colliding, and every once in a while, you get a certain set of collisions that creates a void space. And that void space is like a vapor embryo. And the size of the vapor embryo, it takes more energy to create a vapor embryo, more energy to create to grow that embryo up to a certain point, and then at which point you get spontaneous growth of the vapor embryo. So this is that critical radius, and there's a big difference between C3 and C4. Okay, so these are different radii and different scales, 10 to the -18 to 10 to the -15. And it seems to line up pretty well. So again, if we plot the embryo flux as a function of normalized pressure, if we look at the peak negative pressure in the bubble, that was found from the mechanical index required to activate the particles, we see that it corresponds to this about where the curve crosses that critical new flux. For both C3, here and for C4. So we need a lower heat negative pressure to vaporize C3. You need a higher heat negative pressure to vaporize C4. But it corresponds really quite well, without even having to count for superharmonic focusing, just the room dynamics. And you can also look at that vaporization threshold that we determined in that little chamber, and we look at the embryo flux, and here's the point. So here's the spinodal, and we see that it fit pretty nicely. The data fit that it seems to be vaporizing at the spinodal temperature. So it seems to be fitting both the pressure and the temperature data. Just about to run out of good revenue weeks of putting out on the laser. Okay, so that's pretty in-depth view of droplets. Again, we think that right now our hypothesis is that bubble condensation, you can pressurize the droplet, and the faster the better, and the pressure at which it will condense is slightly higher than the saturation pressure, and that's because equilibrium saturation pressure, that's because of one of two possible mechanisms. On one hand, you have elasticity of the shell that's leading to a pressure drop. On the other hand, you have the homogeneous nucleation of the liquid phase. And then on the other side, when you re-vaporize, the data is very consistent that it's probably homogeneous nucleation, the barrier for homogeneous nucleation, that's leading to the superheated state of the droplet. What I failed to mention here was something really important. So the boiling point of C3F8 is like negative 30 something degrees Celsius. And we have stable droplets at room temperature. Okay, so they're really superheated. The C3F8 seems to be, there's some variability in whether it's stable in vivo or not. When you go to 37 degrees Celsius, but it's like 60 degrees of superheat. But the C4F10, they're definitely stable in vivo, even though the boiling point of C4F10 is like negative 2 or 3 degrees Celsius. But they're stable as droplets in vivo. So they're superheated droplets, and then you add that little bit of acoustic energy, and it's enough that the tension phase of that ultrasound wave is enough to initiate the vaporization. So it's a pretty cool phenomenon. Thermodynamics are awesome. Okay. Any questions on that?